Real-world environments are constantly changing. But for blind and low-vision individuals, these changes are often invisible and can introduce safety risks and cognitive burden. While existing visual assistive technologies can describe immediate surroundings, they operate as one-off interactions and lack persistent memory to surface meaningful changes across revisits. To address this, we present StateScribe, a system that supports accessible awareness of real-world changes across revisits. Users can record on demand or use always-on cameras. Its technical core is a pipeline that detects changes and constructs and updates memory from the live camera view. It employs a dual-layer memory architecture that integrates episodic scene memory and object-centric temporal memory as its core. We used a participant-captured video to illustrate a grocery shopping scenario. As this is their first time visiting the grocery store, they explore the environment while StateScribe constructs an episodic scene memory and provides live descriptions for scene understanding.
I see good wipes next to Chips Ahoy and Oreos on a shelf. I notice a digital display for frozen pizza next to LaCroix. I see Kroger flushable wipes for $8 and Cascade dishwashing pods for $15.
Live descriptions are generated by prompting a vision language model with keyframes from episodic scene memory, which includes RGB and depth images along with camera poses. When revisiting the store a week later, items may have changed. StateScribe detects these changes and announces them to the user.
A Lay's kettle-cooked bag is now on the top shelf at 12 o'clock, about 5 feet away. The space was previously empty. The nearby display changed from a frozen pizza ad to a pet deal ad.
This is achieved by querying the current camera pose to retrieve prior frames with similar poses, and then selecting the most similar view based on overlap area of visibility masks. Using these visibility masks, we identify objects captured in both the current and reference frames, while excluding those at the edges or under occlusion to reduce false positives. Detected changes are back-projected into 3D space, enabling StateScribe to classify them by spatial location as additions, removals, replacements, or attribute modifications, and then update the object-centric temporal memory. This memory architecture allows StateScribe to provide accurate spatial and temporal information.
At your 2 o'clock about 3 feet away, I see Kroger flushable wipes went from $8 to $10, and Cascade pods are sold out. I noticed several changes at your 12 o'clock about 1 foot away. Oreo Thins were replaced by Caramel Coconut Oreos, Good Wipes by Dude Wipes, and Chips Ahoy are sold out.
We conducted a technical evaluation of StateScribe, where we compared to a live model and an offline video model. The live model prompts a vision language model at 1 frame per second to approximate real-time interaction. The offline video model processes a concatenated video as a single input. To simulate extended use, we constructed a dataset of repeated visits to the same environments over time. The dataset includes 3 environments, including a shared office with varying objects on tables, a grocery store with densely arranged items across shelves, and an outdoor courtyard featuring signs and barriers. We found that StateScribe outperformed both baselines in change detection. It achieved an F1 score of 83.1%, substantially higher than the live model and the office video model. When examining the prediction distribution across models, StateScribe achieved the highest accuracy while generating much less repetitive change detections. This trend also extended to spatial accuracy, with StateScribe showing lower clock direction and distance estimation errors. We further evaluated StateScribe's scalability by examining whether latency increases with extended use and how memory usage grows. To this end, we concatenated data from 11 revisits 10 times, yielding 110 visits. Across 110 revisits, object-centric temporal memory remained lightweight, reaching only 55 megabytes. And latency did not increase with memory, as the architecture retrieves only prior visit data from episodic scene memory, discards outdated ones, and stores only essential object changes. Latency is primarily driven by VLM inference, with higher overhead from reference frame matching in grocery scenarios due to dense object layouts. Through a user study with 9 participants in the same scenarios, StateScribe effectively supported participants to detect changes, and participants were impressed by StateScribe's memory capabilities, which are not supported by current off-the-shelf visual assistive technologies. As one mentioned, I'm astounded at how well it remembers and describes differences as you move. That's not something current apps can do. Please refer to our paper for more details.